When we first studied shortest path algorithms, we had two types of algorithms that we used. One of them was the BFS, or breadth first search algorithm, and that basically worked well for an unweighted graph where we could essentially find the shortest distance between a starting vertex and every other vertex, just essentially by looking at all the neighbors and the neighbors and the neighbors and so on. And then we bumped into the circumstance where, well, what if the graph is weighted? We can't exactly just label each edge weight as being the same like we do in BFS, so we needed Dijkstra's algorithm. The same kind of thing applies to finding minimal spanning trees out of a graph, where we can actually use breadth first search again to find a minimal spanning tree. But what happens when we have a weighted graph, right? We're now assuming our edge weights are something greater than or equal to 1, and they're not all going to be the same. We still need to be able to generate a minimal spanning tree. So how do we do that? Well, it turns out that it's a similar concept to using breadth first search. And let's just go ahead and just touch on the algorithm here and see how this works and what this is actually saying. So this algorithm finds a minimal spanning tree if one exists for a weighted graph with n vertices. So we're going to have actually two sets here that we're going to keep track of. One of those is a set of edges, which will be capital T, and L is the set of vertices incident with the edges in T. The reason this is necessary is that we don't create any cycles in a graph. So when we add a vertex to our vertex set, we also need to check the edges to make sure that well, we're not creating any redundancies. In other words, when we're generating a minimal spanning tree in a graph that, say, looks quite simple like this, well, we want to make sure that we don't end up starting here and then making our way around, and then creating an unnecessary loop, because then we don't have a tree anymore. So the idea is, first of all, and we just refer to that here as capital U, and add that vertex to the list of vertices. Okay, and so right now T is going to equal, remember this is the empty set. We haven't looked at any edges to add yet. So rather than deleting edges like we do in BFS, we're actually just going to add. We're going to be very deliberate about adding edges. How are we going to do that? Well, here we're going to kind of keep on doing this step 2. And it says, while some edge has one vertex in L and one not in L. What does that mean? That means that you don't want to consider an edge that has both vertices already in L, because then you are going to end up fabricating a loop. So let's just say, this is vertex A, B, C, and D. And let's say, you start carving out your path like this. And so, okay, well, C is not a vertex in that set, so we add it. And now your set L would include the vertices A, B, and C. And so now what you don't want to do is you don't want to say, oh, well, there's an edge from C to A here, so let me add that. Well, no, that's not going to happen because vertex A is already in that set, so it prevents us from creating a cycle. So while some edge has one vertex that is in L and one vertex that is not in L, choose an edge of smallest weight from among those with one vertex in L and the other not in L. Ties can be broken arbitrarily here. So it's kind of like you get to decide. If a computer is doing this, it's probably just going to pick if there's a tie for 5 for 2 edges, it's just going to pick just the first one that it sees. Okay, then once you've done this, you place the edge in T. Okay, so we keep track of which edges have been added. And the reason we want to keep track of the edges is because, well, you got to know what the minimal spanning tree is going to be. And just by adding the vertices doesn't necessarily tell us what edges those correspond to. Place its vertices in L. Okay, so we're going to populate the T set, we're going to populate the L set. Later on, we're going to be able to use the T set. Now, step 3 is, okay, well, if the size of L, okay, remember L is going to contain all the vertices that we've accounted for. If the size of L is smaller than N, in other words, if the vertices that you've added is less than the number of vertices in the graph is not connected, and so it has no minimal spanning tree. Remember, that's one of the things that you have to have is you have to have a connected graph. So that's just an important check to have in your algorithm. Otherwise, the edges in T and their incident vertices form a minimal spanning tree. Okay, let's go ahead and execute this and see how pretty straightforward this actually is to pick. Now, we do have to pick a starting vertex. So your minimal spanning tree will start with the vertex that you pick. Let's go ahead and start with vertex A. Okay. It doesn't matter. Let's just say we're interested in starting with vertex A, though. And I'm also going to keep track of T. Okay, so look at the vertices that are incident to A, that are adjacent to A, but not already in set L. Well, there's no other vertices in set L right now. So A connects to B, A connects to C. Of those two edge weights, we see that 3 is smaller. So we're going to add the edge AC to our what we're going to generate as a minimal spanning tree. Now we do see that this one is connected. So in step 3, if the size of L, well, it will actually end up being equal to N. So we're going to run the otherwise. The edges in T and their incident vertices form a minimal spanning tree. Okay, so that means that what I've just done is I've added AC. That's going to be part of my minimal spanning tree. Not AB, right? Because AB is actually, that's a longer edge. And if these edge weights represent something like distances, and maybe what you want to do is these are all some sort of, I don't know, internet servers, and you really want to kind of minimize the distance between servers that are going to communicate. So, we can still get B into the loop, but maybe we just need to make sure that every server connects, can be traced back to this starting server right over here. But we want to do that in, these could be costs, maybe, so we want to minimize cost or we want to minimize distance. Okay, so now we would add vertex C to our list of vertices. Okay, from there, so let's see what the algorithm says. It says, okay, while some edge has one vertex in L and one not in L. Well, some edge has one vertex in L and one not in L. Okay, well, let's see. CA does not have one vertex in L and one vertex not in L because both C and A are already in that list, so that prevents us from reconsidering an edge that's already done. Now, we do still have AB. That's still going to be a consideration because that's not creating a cycle, right? We do need to get B in as part of this path, but I'll consider AB because AB is an edge that has one vertex in L, and, well, B it's not in L, so that would be a valid edge to consider. Then I have CB. Well, already CB we see that is shorter than AB, so we're not going to add AB to the set because, well, we could get B to be part of that without that extra expense. Now we also have CD, which is an edge weight of 5. Well, that's bigger than an edge weight of 4. CF has an edge weight of 6. That's the biggest of all of them. So at this point, we're going to pick the edge with the shortest weight, which will be CB. So now we're going to add B to the set of visited vertices, and therefore, now this may not always pan out linearly, and if you're like, well, can't I just keep track of the vertices and that will tell me like AC, CB are going to be the edges? Not necessarily, because sometimes we may hop back to another vertex that at the moment has the shortest edge weight or the smallest edge weight. So right now we will add CB, and right now it looks like we're going along a linear path. That may not always be the case. Great. At this point, consider the edges that have one vertex in L and the other not in L. So let's consider vertex A. Well, the only vertex that has an edge from A to it is B, but that is already in our set L. So in a sense, vertex A is not one that we're ever going to consider again because vertex A doesn't have any more vertices that are adjacent to it that are not already in our list. Okay, now we look at all the neighbors of C. Well, we have CD and CF. That's an edge weight of 5 and an edge weight of 6. So notice how we could come back to vertex C now because it is a vertex that is in L, and it does have vertices that it is adjacent to that are not yet in L. So we have CD, we have CF, 5 and 6. So 5 is the lowest so far. Now consider vertex B. So B has a neighbor of D, which is 6. That's too far. That's longer than 5. But then there's BE, which E is not yet in the list. And look at that edge weight. It's a lot lower than any of the others. So at this point, we're going to add BE to that set, and now we're going to add vertex E to our list. Okay, now notice that every time we jump back to the next stage, we always go back as far as we can. So we'll still consider vertex C, we'll still consider vertex B, but we'll also now consider vertex E. Okay, so vertex C still has two neighbors that are not in L. C to D, that's the winner so far. That's the lesser of the two. B just has D now. D is not inside of L, but that's a distance of 6. So we don't want that. Let's consider vertex E. Well, there's E to D, which is a weight of 6. That's bigger than our winner so far. And then we have E to F, which is a distance of 3. And of course, a distance of 3 is the lowest. So we're going to pick the edge EF. And you can see so far we're not, the reason, we're not going to consider F to C now because F and C are already, add F in here, F and C are already both inside of the vertex set. So there's no way that this will accidentally get added, even if 6 ended up being the smallest edge weight at some point throughout our process. Now we still have two vertices that we don't have tied into this spanning tree, which is D and G. So what would happen next? Well, now we would again consider vertex C. What are the neighbors of C that have not been added yet? Well, D and F. But of those two, C to D is the shortest. So 5 is the one to beat right now. Let's now look at vertex B. Well, vertex B only has D that is adjacent to it, not part of the list yet. That's bigger than the 5, so that right now is not even a considered candidate that we're going to consider. What about E? Well, E has E to D, which is 6. Okay, it's bigger than the 5. Then we have E to G. Well, that's a tie right now for C, D, and E to G. So we could arbitrarily pick one of them, assuming that that's going to be a tie for the smallest. But I still have to consider the neighbors of F that are not yet inside of the list. We have F to D, which is 6. Okay, that's bigger than 5. But then we have F to G, and F weight of 4, so we're going to add F to G. But yeah, that one. Oh yeah, we did because it's going to be the tie for 5 units. So F to G, we are going to add that. And again, right now it looks like we're carving out a linear path, but you'll see in a moment that that is not going to be the case all the way around. So now we add G in, and notice that we still have one vertex left, vertex D, that needs to be considered. And now, again, we have to go all the way back. What are the neighbors of C? Well, there's C to D, and C to F we won't consider because, remember, F is already in the list. If we added C to F, then we would have, obviously, we'd have a loop here in the center. Then we have B, B to D, that's bigger than 5. E to G, don't want to consider that because E and G are already in the list. Then we have, what did I say? I already say E to D. E to D is 6, that's bigger than C to D. F, well, we could go F to D, but that's 6. And then we could go G. Well, G doesn't have any neighbors that aren't yet in the list. Therefore, of the shortest, notice that C to D was the shortest. So CD is going to be added. Vertex D gets added to this set. And remember, we keep doing this. This is a while statement. While some edge has one vertex in L and one not in L, at this point you see that all of the vertices are in list L, which means we have a tree, and we can close off these sets. Now notice how I mentioned earlier, just because you add in the vertices in a certain order doesn't mean that those are the same pairs of edges that get added. So we had AC, and we had CB, and then BE, EF, FG, but then notice that our last vertex was not GD, it was CD, and that's why we have to keep track of these two sets. This keeps track of all the ones that we visited, and this actually gives us our minimal span tree. So there it is. So now the reason I wanted to kind of highlight these is to show that from this set T, we could generate this graph. And if you notice that it is a tree, it's all connected. You can get from any vertex to every other vertex, and simultaneously there are no cycles. Now, if you wanted to redraw this to see it, you could put vertex A at the top, and then C, B, and D, C, B, and D, B and D, and then from B to E, B to E, E to F, and F to G. So there's our minimal spanning tree, and then of course we can label all of these edge weights. This is 3, 4, and 5, and then we have 2. E to F is 3, F to G is 4. So if our objective was to minimize if these were costs, we have just minimized the total cost of creating a tree out of a graph. Let's go ahead and do one more just to kind of emphasize this. And in this particular question, let's go ahead and start with capital S. It sounds like the starting vertex. Okay, so we'll add S into here, start building our set T. So we only have S to C and S. Of those, S to C is the shortest, so SC becomes an edge in our graph, and we add C to this set. We go back, now there's SE is a weight of 4. Now we have C as well. C to E is 1, C to F is 3, C to D is 5. Of 4, 1, 3, and 5, 1 is the shortest. So now we would add the edge CE to our graph, and we would add vertex E as being accomplished. Okay, now S, well, S has no vertices as neighbors that are not already part of set L. So I'm just going to put a little X above that to help me remember that's done. Now I have C, so C to D is 5, C to F is 3. 3 is shorter of those two, so right now I'm looking for a competitor to a distance of 3. But now I have vertex E, its neighbors are F and J. F is 1 unit away. That's lesser than 3, so far E to F is the one that's going to get added. E to J is 2, that's bigger than 1. So E to F is the edge that I want to add. And once again, we go back. Vertex C, what are its neighbors? F and D. F is the shortest so far. Then we want to look at vertex E. Okay, E to J is a distance of 2. That's smaller than 3. So far 2 is the winner. And then F, well, now I can only go F to G, which is 2, or F to D, which is 3. Not F to C, because C's already been added. Otherwise, I'd create a little triangular loop here. So notice I have a tie. I have a tie for F to G, which is 2, and E to J, which is 2. So in this case, you arbitrarily pick a tiebreaker. Because E to J was the first one I said, I'm going to go ahead and pick that one. But it doesn't matter because F to G would also give you 2 more units of expense, just like E to J would. Okay, so notice again that we're totally nonlinear here, right? Because we kind of carved out the path S, C, E, F, but then we went E, J. E, J gets added. Add J to that list. Back to the beginning. C to D. We no longer have C to F because F has been added to our vertex set. We do not want to create a loop. So 5 is the one to beat. E is done. It has no unlabeled or no neighbors that aren't in the list. F to G is 2. That beats 5. So right now 2 is the one to beat. F to D is 3. It's not shorter. And now J to G is 3. That's not shorter either. So of those, F to G is the shortest. And we'll add that into our list. And we'll add vertex G into our set here. We have 3 more vertices to go. And now, again, we jump back to vertex C. So C to D is 5, because D has not been resolved yet. So 5 is the one to beat. E, okay, E is done. F to D is 3. That's shorter than 5. So right now, the distance to beat is 3. F to D. J, okay, J has no neighbors that aren't already part of the set. And then G to D is, well, look at that. G to D is 1. That beats 3. G to H is 3. Therefore, G to D is the edge we want to add. D is now done. Again, we jump all the way back to the beginning. C, well, C has all of its neighbors already added to this, so there's no other vertices that C is adjacent to that aren't already part of our list. E is the same. E is the same. F is the same as well. J is the same. G, okay, well, G has an unlabeled, or a neighbor that hasn't been added to the list, G to H, so 3 is the unit to beat. And then D, well, D to H is 1, which is shorter than 3, and so we want to go ahead and add D to H. D to H. All right, almost done. Now, there's actually, you probably already see this, but there's only one edge left that corresponds to an adjacent vertex that is not yet part of our list. That's going to be H to A. In fact, we don't even have to go back S, C, E, F, and J because those don't have any neighbors that aren't part of it yet. G, same thing now, G to H. That's no longer a possibility because we create a cycle. And then now, oops, we forgot to add H over here. D, same thing. D has no neighbors that aren't part of the list. D is done. H to A is the only one, and so that's going to get added to our edge set. So here's our minimal spanning tree. It's right there. And you can see how that carves out nice and beautifully where we now have a spanning tree made out of a graph that is minimal for a circumstance with weighted edges. And that's pretty much how Prim's algorithm works.